Imagine you throw a ball straight ahead, and instead of flying where you aimed, it drifts sideways. Not dramatically, barely enough to notice, but consistently in the wrong direction. You'd want to know why. That's exactly what's happening with 3I, Atlas. It's drifting sideways not enough to significantly alter its path through the solar system, just enough that over a month, the total offset equals about half the radius of the Moon. Negligible in cosmic terms, yes, but the direction of this push defies standard predictions from cometary physics. To understand why, we need to unpack the very fundamentals of force in space, how scientists measure motion with extraordinary precision, and what the geometry of 3I, Atlas's jets, reveals about the processes inside this object. Today, we'll build the story from scratch. No shortcuts. We'll start by understanding what non-gravitational acceleration is and why it exists. Then we'll examine NASA's official model, contrast it with a recent paper published in March 2026, analyze what the jet geometry tells us, and finally, address the question that drives this entire discussion: is the sideways push natural, or does it require a more exotic explanation? The answer isn't simple, but by the end, you'll have the tools to think critically about it yourself. First, remember, gravity isn't the only force in space. For a dead, inert rock drifting through the cosmos, gravity is essentially the whole story. Measure its position and velocity, apply Newton's laws with Einstein's corrections, and you can predict its future path with astonishing accuracy. Observations match predictions to within tiny measurement errors. But comets are not inert. They're active. As they approach the sun, solar radiation heats their surfaces, sublimating ice into gas. And here's the key: when gas escapes in one direction, it pushes the nucleus in the opposite direction. Newton's third law in action. This push is called non-gravitational acceleration. It's real, measurable, and conceptually straightforward. Every active comet experiences it. How do scientists measure it? By comparing where a comet actually is with where it would be under pure gravity. If the comet drifts slightly ahead, behind, or sideways, something is pushing it. Months of careful astrometric observations reveal the magnitude, direction, and how this push changes with distance from the sunday. The standard mathematical framework comes from Brian Marsden, Zing Sina, and Donald Uman in 1973. They broke the push into three components: A1, pointing toward or away from the sun; A2, along the comet's orbital motion; and A3, perpendicular to the orbital plane. These numbers A1, A2, A3 are at the heart of the debate over 3I, Atlas's non-gravitational acceleration, their size, ratios, and what they reveal about the physics driving the push. Before examining 3I, Atlas, we need a baseline. What should A1, A2, and A3 look like for a typical comet? Solar heating drives outgassing. The sunward side of a comet is hottest, sublimating gas most vigorously. For a perfectly spherical comet with uniform ice and no rotation, gas escapes evenly from the sun-facing hemisphere, producing a push directly away from the sunday. That's A1. Real comets rotate and have uneven surfaces with active regions called source areas. While these complicate things, the radial push usually dominates, making A1 much larger than A2, which remains small. NASA's official report on 3I, Atlas, reflects this standard picture. A1 is roughly 5 times larger than A2, showing a primarily radial push. But a new paper by Spatata, Krauska, and Dones tells a different story, raising questions about the sideways component that standard models might not fully capture. Understanding their disagreement requires first appreciating the challenges of measuring non-gravitational acceleration in such tiny, distant objects, a story we'll explore next. Measuring non-gravitational acceleration in an object like 3I Atlas is incredibly delicate. The positions of objects in space are determined using astrometry, recording their precise locations in the sky as right ascension and declination. Modern instruments can pinpoint these positions to fractions of an arcsecond. Yet, the non-gravitational acceleration of 3I Atlas is tiny, about 1 micrometer per second squared at Earth's orbital distance. Over a month, that produces a lateral shift roughly equal to half the Moon's radius, minuscule compared to the distance from Earth to the Sunday. Detecting this subtle signal demands months of measurements, carefully accumulated and cross-checked. Each observation carries uncertainties. Atmospheric effects, telescope calibration, and even tiny errors in reference star positions all introduce potential discrepancies. Over time, with many observations spanning months, scientists can filter out random noise and begin to constrain the true acceleration. But 3I Atlas presented a unique challenge. In October 2025, it passed behind the Sun from Earth's perspective. During this solar conjunction, ground-based telescopes could not observe it, leaving a critical gap precisely when the object's outgassing and thus its non-gravitational acceleration was most intense. This missing data divides observations into two arcs, pre- and post-perihelion, forcing scientists to make assumptions to model the acceleration across the gap. Different assumptions produce different results, particularly for A2, the transverse component along the orbital path. A1 and A3 remain relatively robust because they dominate the overall deviation and are less sensitive to modeling assumptions. A2, however, depends heavily on how scientists interpolate behavior during perihelion, how they weight each observation, and which mathematical form they assume for the outgassing's distance dependence. Both NASA and the Spatata team are aware of these complications, which explains why their results for A2 differ. NASA's model, developed by David Farinocchia at JPL, relied on 782 high-quality astrometric observations. JPL applies strict quality filters, excluding measurements that don't meet precision standards. The dataset is smaller but cleaner. Initially, the model used the standard water-ice sublimation formula, which assumes outgassing drops steeply with distance from the Sunday. Later, recognizing that CO2 dominates 3I Atlas's activity, the model switched to a milder CO2-based distance dependence. This approach produced an A1 roughly 5 times larger than A2, consistent with a radial, sunward-directed push. But an intriguing historical note complicates this picture. In late 2025, Avi Loeb noticed that 3I Atlas's predicted closest approach to Jupiter in March 2026 was just within Jupiter's Hill radius, the boundary where Jupiter's gravity overtakes the Sun's. He emailed Farinocchia about this, but received no response. Within days, JPL revised A1 downward and adjusted the sublimation model, placing the object slightly outside the Hill radius. Loeb reported this change publicly, noting that the perihelion data gap meant the revised prediction's accuracy could not be independently confirmed. Meanwhile, the Spatata, Krauska, and Dones paper, posted in February 2026, approached the problem differently. Their dataset included 7,788 astrometric observations, 10 times more than NASA's. Rather than filtering aggressively, they incorporated a broader set of observations with a carefully constructed error model. They tested multiple functional forms for outgassing, including symmetric, time offset, and asymmetric models reflecting the comet's observed fading after perihelion. Across all models, A1 and A3 remained consistent, but A2 differed significantly, especially in the asymmetric cases. The result, the transverse push, A2, is comparable in magnitude to A1, suggesting 3I. Atlas is being pushed sideways nearly as much as radially. This is where the story becomes particularly compelling. The Hubble Space Telescope offers independent confirmation. Imaging reveals 3 mini-jets on 3I, Atlas, spaced precisely 120 degrees apart, wobbling with a period of 7.1 hours, the nucleus's rotation period. The orientation of these jets matches the spin axis roughly 20 degrees off the sunward direction, providing a physical mechanism for a substantial transverse push. 2 independent measurements, orbital deviation and direct imaging, converge on the same conclusion. 3I, Atlas is not just being pushed away from the Sun, it's drifting sideways in a way that challenges simple cometary expectations. To understand the sideways push, we need to look closely at what it means physically for A2, the transverse component, to be comparable to A1, the radial component. Normally, cometary outgassing is strongest along the Sun-comet line. The sunward side heats the surface, sublimating ice, producing gas that escapes directly away from the Sunday. That generates a radial acceleration. A1 dominates, and A2 is much smaller. But 3I, Atlas, breaks this pattern. For A2 to match A1, the gas must escape in directions partially along the orbital motion, not just directly away from the Sunday. 2 natural mechanisms could produce this effect. The first involves the comet's spin axis orientation. 3I, Atlas rotates, and its spin axis points roughly 20 degrees off the sunward direction. In this orientation, regions near the rotational poles receive nearly constant sunlight, while equatorial regions experience variable illumination. Jets emerging from high-latitude regions near the pole emit gas roughly along the spin axis, which is close to, but not exactly along the Sun-comet line. If the axis wobbles or precesses, the transverse component averages over a range of directions, producing a systematic sideways push. The second mechanism involves localized active regions. Comets are rarely uniform. Ice exposure is uneven due to cratering, erosion, or fractures. Gas escapes preferentially from these active areas. Thermal lag also plays a role. The peak sublimation often occurs slightly past the subsolar point because the surface stores heat, releasing it gradually. Depending on the nucleus's orientation and rotation, these asymmetrically placed jets produce a transverse acceleration. Hubble Space Telescope imaging confirms this picture. Avi Loeb and Tony Scarmato analyze high-resolution images using a rotational gradient filter, which subtracts the symmetric coma background, highlighting asymmetric structures. They discovered 3 mini-jets, evenly spaced at 120 degrees, and a fourth, more prominent sunward jet known as the anti-tail. The mini-jets wobble with the nucleus's 1-hour rotation, showing a periodic and coherent pattern, not random emissions. From the jet wobble, they derived a spin axis orientation within 20 degrees of the Sun, consistent with the observed transverse push. The geometry is compelling. 3 jets around a nearly sunward pole produce gas emission not purely radial. Combined with the nucleus's rotation, this creates an aggregate push both outward and sideways, matching the magnitude of A2 inferred from orbital deviations. In other words, the sideways acceleration observed by the Spadada paper is physically consistent with what Hubble imaging reveals. 2 independent lines of evidence converge: orbital deviations and direct observation of jets. Yet, some features remain unusual. The 120-degree spacing of the jets is enigmatic. Natural active regions form where ice is exposed, but no physical mechanism inherently produces three perfectly spaced jets. Loeb calls this pattern enigmatic, meaning we observe it but cannot fully explain it with standard cometary physics. Even so, the natural explanation is coherent. Spin axis orientation plus asymmetric, localized jets could produce the observed transverse acceleration. This understanding frames the broader debate. While the natural explanation is plausible, some anomalies remain, including unusual chemical ratios, post-perihelion eruptions, and a near-Hill radius encounter with Jupiter. Individually, these features can be explained. Together, they raise questions about whether natural processes are sufficient or if alternative explanations should be considered. One alternative explanation proposed is the propulsion hypothesis. Avi Loeb and colleagues have considered the possibility that 3I, Atlas, might be an artificial object with an active propulsion system. Loeb frames this cautiously, emphasizing it as an open question, not a conclusion. To evaluate this, we must examine what such a hypothesis would require. For propulsion to account for the observed transverse acceleration, the object roughly 2.6 kilometers in diameter, traveling at 58 kilometers per second, would need an active system capable of producing a sideways push matching the natural outgassing signal. The total non-gravitational acceleration is tiny, just 1 micrometer per second squared, but it would need to be sustained over months in a precise directional pattern. The jets observed at 120 degrees spacing could theoretically be engineered thrusters designed for attitude control, as three non-coplanar forces are typically needed to maintain orientation. The propulsion hypothesis also raises questions about 3I, Atlas's comet-like activity. Its water outgassing, dust coma, and molecular composition could either be genuine cometary processes, coincidentally masking an artificial object, or part of a cloaking or propulsion system designed to mimic natural outgassing. However, no radio or technosignatures were detected by the Green Bank telescope in December 2025, which does not rule out a non-transmitting object, but removes one direct line of evidence for technological activity. The natural explanation, in contrast, requires fewer assumptions. It relies on known cometary physics, high-latitude active regions, spin axis orientation, and asymmetric jet emissions. These elements are individually plausible, and together they can explain the observed transverse acceleration. But even this scenario has gaps. The perfect 120 degrees spacing of the mini-jets is unexplained, as natural processes do not inherently produce such geometric regularity. Likewise, the combination of unusual chemical ratios, deep interior eruptions, and post-perihelion fading is uncommon, though not impossible for a natural object. The upcoming Jupiter flyby on March 16, 2026, provides a rare opportunity to test these models. The planet's gravitational deflection is predictable with high precision. Depending on which orbital model is more accurate, NASA's radial-dominated solution or the Spatata paper's large transverse component, the post-flyby trajectory will reveal subtle differences. Within weeks, new astrometric observations will refine the models, narrowing the uncertainties around what is pushing 3I Atlas sideways. For now, the facts are clear. 3I Atlas is subject to measurable non-gravitational acceleration. Its total magnitude is tiny, but the direction is under debate. Hubble imaging confirms the presence of 3 symmetric jets and a spin axis near sunward consistent with a transverse push comparable to the radial component. The natural explanation is physically coherent, though the 120-degree spacing is enigmatic. The propulsion hypothesis remains speculative but cannot be completely ruled out without further data. The object is chemically unusual, geometrically surprising, and dynamically complex, like nothing else observed from outside our solar system. Its behavior challenges conventional expectations for comets, yet does not violate physical principles. In 9 days, 3I Atlas will leave the solar system, and the Jupiter encounter will provide critical data that sharpens the picture, though it may not close the debate. Let's now assemble the natural explanation for 3I Atlas's sideways push as clearly and charitably as possible. The nucleus has a spin axis oriented about 20 degrees off the sunward direction, and 3 localized active regions, likely exposed ice sources, are symmetrically spaced at 120 degrees intervals around the nucleus. As it rotates, gas from these high-latitude jets escapes in directions slightly off the Sun-comet line. The resulting net push is both radial and transverse, producing A2 and A1 of comparable magnitude. The Spatata paper's findings match this model. The orbital signature of the transverse acceleration aligns with the observed jet geometry. 2 independent lines of evidence converge, reinforcing the natural explanation. Each component of this explanation is plausible. Active regions on cometary nuclei exist, spin axes near sunward orientation are known, and localized jets producing non-radial acceleration are observed elsewhere in our solar system. Yet, 2 features remain particularly striking. First, the perfect 120 degrees spacing of the mini-jets is unusual. Natural processes do not inherently produce 3 equally spaced active regions. Loeb calls this enigmatic, meaning we observe it but cannot fully explain it with standard cometary physics. Second, the combination of anomalies, the sideways acceleration, the CO2 to water ratio 4.5 sigma above the solar system norm, methanol 4 times higher than typical, deep post-perihelion eruptions, and a near-Hill radius Jupiter encounter is extraordinary. Individually, these features can be explained. Collectively, they raise questions about plausibility. The propulsion hypothesis attempts to address these gaps. It would require an object roughly 2.6 kilometers in diameter, traveling at 58 kilometers per second, equipped with a propulsion system producing a sustained directional transverse acceleration. The 120 degrees jets could represent thrusters designed for attitude control, while the cometary activity could either be coincidental, natural outgassing, or a manufactured facade. The hypothesis must also account for the absence of detectable radio emissions, a limitation that weakens the evidence but does not fully rule out the possibility. Ultimately, the data available today cannot decisively confirm either scenario. Science can construct plausible natural explanations, and it can outline hypothetical artificial scenarios, but it cannot yet close the debate. That is the honest, evidence-based position. What is clear is that 3I Atlas is chemically unusual, geometrically striking, and dynamically complex, the most extreme object we have ever observed from beyond our solar system. It challenges conventional cometary expectations, but remains within the realm of natural possibility. The Jupiter flyby will provide a rare, high-precision test. Observations of the object's trajectory before, during, and after the encounter will allow astronomers to compare predicted paths from NASA's radial-dominated model and the Spatata paper's transverse-inclusive model. Differences in deflection and post-flyby trajectory will reveal which model better represents reality. Even so, the flyby will constrain, not resolve, the debate. Science often leaves questions open, narrowing the range of plausible explanations without demanding premature conclusions. In summary, here is what we actually know. 3. Atlas is experiencing non-gravitational acceleration. It is not following a purely gravitational trajectory. The total magnitude of this push is minuscule, 1 micrometer per second squared, producing a lateral shift of only half the Moon's radius over a month. Small enough to be negligible for navigation, yet significant for understanding the physics involved. The direction of the push is under debate. NASA's official model, based on a smaller, highly vetted dataset, finds a primarily radial acceleration, a 1.5 times larger than A2. The Spatata paper, using 10 times more observations and asymmetric outgassing models, finds A2 roughly equal to A1. Hubble imaging corroborates this, revealing 3 mini-jets at 120 degrees spacing around a spin axis, roughly 20 degrees from the Sun, wobbling with a 7-1-hour period. The geometry is physically consistent with a significant transverse acceleration. 2 independent lines of evidence, the orbital deviation and direct imaging, converge to suggest a sideways push. The natural explanation is plausible and internally coherent, yet not without enigmatic features. The perfect 120 degrees jet spacing is unexplained, and the simultaneous occurrence of multiple anomalies, the unusual molecular composition, deep post-perihelion activity, and the close Jupiter encounter is statistically unusual. The propulsion hypothesis could account for these patterns, but requires extraordinary assumptions, sustained directional thrust, deliberate jet placement, and either coincidental or engineered comet-like activity. Importantly, no direct technological signatures have been detected, leaving the hypothesis speculative. Science, by its nature, accepts uncertainty. The available data constrains possibilities, but does not fully resolve them. 3. Atlas is the most chemically unusual, geometrically surprising, and dynamically complex interstellar object we have ever observed. It does not behave exactly like a solar system comet, but it also does not behave in ways that are impossible for a natural object. Its departure from the solar system in just 9 days, combined with the upcoming Jupiter flyby, offers a rare opportunity to test models with high precision. Observations will refine orbital predictions, narrow uncertainties, and sharpen our understanding of what drives its motion, but they will not instantly answer every question. In the end, the sideways push remains an open mystery. The natural explanation, high-latitude jets, spin axis orientation, and asymmetric outgassing, is consistent with observed data, while the propulsion hypothesis provides a framework for the unexplained 120-degree symmetry and anomalies. Both are plausible, neither is proven, and the truth likely lies somewhere between what we can measure, model, and imagine. If there's one thing to take away, it's this. 3. Atlas challenges our assumptions about interstellar objects, cometary physics, and the limits of natural versus artificial explanations. It is a testament to the power of careful observation, independent verification, and the scientific method itself. If you found this exploration fascinating, make sure to like, subscribe, and hit the notification bell. Join us as we follow 3I Atlas on its final journey out of the solar system, and stay tuned for updates on what the Jupiter flyby reveals, because the story of this mysterious interstellar visitor is far from over.